And one of the things that I found that's really fascinating in this arena is the notion of composition, and it's really it's a funny kind of notion because in some sense it's very natural. We've all played with tinker toy like objects. We all understand assembling systems out of smaller systems, and yet there's a dialectic that happens sort of in individuals and in human organizations and happens throughout the history of science. And the Newtonian dynamics is again an excellent example of what goes on here. The question is, typically as we as we approach a given situation where we would like a desired outcome. We'd like to make a prediction. We'd like to avoid some risk. We'd like to promote a set of circumstances from one likelihood regime to another. Typically, what we'll do is we come up with a solution that implicitly says we can see the whole system. We can see the whole set of parameters, inputs, outputs. We have some God's eye view. And that's exactly what goes on in models with ordinary differential equations. And there are very serious issues with having to deal with boundary conditions and sort of what's the container of our model. And it sort of in the progression of our development, as long as we have to deal with handfuls of instances of these kinds of situations where we're trying to establish a desired outcome, we cannot. It's okay. It's okay to have a God's eye view, but the point at which we have to deal with hundreds, thousands, millions of instances, or instances in which interactions of our situation with some environment causes nonlinear dynamics. In either of those kinds of paradigms, the God's eye view doesn't work. It can't work. And so one of the interesting sets of tools in the toolbox is being able to think about systems in terms of partial descriptions and building up more and more complete descriptions out of what we can see at the time. So I make a model, you make a model, and we're modeling sort of independent subsystems, and then we get a model of a larger system by putting the two models together. So there's a lot like what we do physically. If I have some chemical and you have another chemical, we can imagine what it means to mix the two chemicals together. We can observe that. And what would be nice is to have mathematics work that way. So I make a model, you make a model, we mix the models like we mix the chemicals. So that notion of composition again shows up in this computational framework, so the computation as interaction. And that changes the game. It completely changes the game. It makes possible, it makes certain calculations and certain modeling efforts possible that were not possible before. And that's a practical reason. But it also has this other side to it, this philosophical side, that is about our development as cognitive beings, as beings that are able to reason about their environment. Individuals have problems with notions of composition. Even people who are steeped in this sort of more modern idea of composition and even parameterized composition can often fall into this trap of needing a God's eye view. Likewise, organizations have this, and the God's eye view paradigm can persist for hundreds of years. So, and it's really quite interesting because if you think about it in a social context, the idea of autonomy and having individuals work together autonomously without some overarching or governing framework or body is a radical notion, and so it's also radical in the mathematics, and that's quite intriguing. So these are some of the ideas that we're going to look at through this series. So I'm going to introduce sort of both informally and then formally some notion of computation that involves sinus infection. That involves computation as interaction. I'm going to enrich that notion with the notion of introspection. And then I'm going to look at modeling various physical situations and then expand that out to what becomes possible in terms of our conceptualization of the physical world. This is probably as good a place as any to stop.